Welcome to a webcast made by the Learning Enhancement team based in the Dean of Students office at the University of East Anglia. This webcast is part of the Steps into Discrete Mathematics series and concerns basics of sequences. This guide introduces the mathematics of sequences and some of the language that describes them. It looks at arithmetic and geometric sequences in more detail. Introduction. When you write down a list of numbers, you are creating something which is called a sequence by mathematicians. Each number in the list is called a term of that sequence, and the terms are separated by commas. Although any list of numbers can be a sequence, usually there are rules which tell you what numbers you can write down. For instance, if you write the positive integers, also called the natural numbers, starting at 1 and ending at 4, you get the sequence 1, 2, 3, 4. The rules would be that 1. The sequence starts at 1. 2. You get the next term in the sequence by adding 1 to the previous term, and you stop when you get to 4. Sequences which stop are called finite sequences. Alternatively, you could write down all the natural numbers starting at 1. 1, 2, 3, 4, and so on. Here the rules would be 1. The sequence starts at 1, and you get the next term in the sequence by adding 1 to the previous term. You use the ellipsis symbol, this, 3 dots only, to indicate that the sequence continues indefinitely. Sequences which do not have an end are called infinite sequences. You can also use an ellipsis to fill in the gap of a long series. For example, the sequence of positive integers from 1 to 20 can be written as 1, 2, 3, 4, ellipsis, 19, 20. Sequences with a pattern. The majority of mathematical sequences follow a strict pattern or recipe. They have a formula for you to follow to generate each term. This recipe is usually given in terms of a number n, sometimes k, and you generate the terms in the sequence by substituting the positive integers, starting with 1, into the formula for n. A sequence which follows a formula is often denoted by Sn, where the S is for sequence and the subscript n tells you that the specific term in the sequence. Example. Write down the infinite sequence defined by Sn equals 3 multiplied by n subtract 1. To find the sequence, input the positive integers into the formula beginning with 1. When n equals 1, 3n minus 1 equals 3 multiplied by 1 minus 1, which equals 2. So, S1 equals 2. When n equals 2, 3n minus 1 equals 3 times 2 minus 1, which equals 5. So, S2 equals 5. When n equals 3, 3n minus 1 equals 3 multiplied by 3 minus 1, which equals 8. So, S3 equals 8. When n equals 4, 3n minus 1 equals 3 times 4 minus 1, which equals 11. So, S4 equals 11, and so on. The general term of this sequence, 2, 5, 8, 11, and so on, is Sn equals 3n minus 1. Arithmetic sequences. You may have noticed in the sequence Sn equals 3n minus 1 that you can make the next term in the sequence by adding 3 to the previous term. It is important you know which number to start with. In the case of Sn equals 3n minus 1, the first term is S1 equals 2. But if you do, you can generate all the terms in the sequence. This number is often denoted by A. A sequence which can be generated by adding the same number, called the common difference, to the previous term is called an arithmetic sequence. Let's look at the sequence Sn equals 3n minus 1 again. When n is equal to 1, the term Sn is called S1. It's equal to 2 plus 0 times 3, or 2, and the term in the sequence is 2. When n is equal to 2, the term in the sequence is called S2. The value is 2 plus 1 multiplied by 3, which is 2 plus 3, which is 5. When n is equal to 3, the term is called S3. It is equal to 2 plus 2 times 3, which is 2 plus 6, which is 8. When n is 4, the term is called S4. It is 2 plus 3 times 3, which is 2 plus 9, which equals 11. This continues. The nth term, called Sn, is 2 plus n minus 1 multiplied by 3, which is the same as 3n minus 1. The first term is 2 plus 0 times 3. The second term is 2 plus 1 times 3. The third term is 2 plus 2 times 3, and so on. Notice that the multiple of 3 you add is 1 less than the term number, and so the nth term is 2 plus n minus 1 multiplied by 3. It is true that, for all arithmetic sequences, the general or nth term is the first term, a, plus n minus 1 multiplied by the common difference, d. As an equation, Sn equals a plus n minus 1 times d. You can use this formula to generate any term in an arithmetic sequence, as long as you know the first term and the common difference. This saves a lot of time and effort, as you do not need to generate the whole sequence. Example: what is the 50th term in the sequence Sn equals 3n minus 1? In the sequence Sn equals 3n minus 1, the first term a equals 2 and the common difference d equals 3. You need to find S50, and so n equals 50. Using the formula, S50 equals 2 plus 50 subtract 1 multiplied by 3, which equals 149. You can also write an arithmetic sequence as Sn plus 1 equals Sn plus d. So the next term in the sequence, Sn plus 1, is generated by adding the common difference to the previous term, Sn. When you write a sequence like this, the formula is called a recurrence relation. Geometric sequences. You have seen that, to get to the next term in an arithmetic sequence, you add a number d to the previous term. In another common type of sequence, a geometric sequence, you multiply the previous term by a number called the common ratio, which is usually written as r. For example, starting with the number 3 and with r equals 5, you get n is equal to 1, so the first term is S1, 3, which is 3. In the sequence it's 3. When n is equal to 2, the term is S2, that is 3 multiplied by 5, which is 15. When n is 3, the term S3 is 3 multiplied by 5 multiplied by 5, or 3 times 5 squared, which is 75. When n is 4, we have S4, which is 3 times 5 times 5 times 5, which is 3 times 5 cubed, or 375. So the nth term, Sn, is 3 multiplied by 5 to the power n minus 1. Each time you multiply the previous term by 5, and so for the second term you have multiplied 3 by 5, for the third term you have multiplied 3 by 5 squared, and for the general term you have multiplied 3 by 5 to the power n minus 1. So, in general, the nth term can be written as Sn equals a multiplied by r to the power n minus 1. You can also write a geometric sequence as the recurrence relation Sn plus 1 equals R multiplied by Sn. So the next term in the sequence, Sn plus 1, is generated by multiplying the previous term, Sn, by the common ratio R. Example. The first term of a geometric sequence is 2, and the seventh term is 1458. What is the common ratio R? The first term is a equals 2, and when n equals 7, the seventh term, the term is 1458. So, putting these values into the formula for the general term, you get S7 equals 1458, which equals 2 multiplied by R to the power 7 minus 1. Dividing by 2, you find that R to the power 6 equals 729. Taking the sixth root, you get R equals the sixth root of 729, which equals 3, or minus 3. This means that there are two geometric sequences which have a first term of 2 and a seventh term of 1458. Common ratio of 3 gives 2, 6, 18, 54, 162, 486, and 1458. The common ratio of minus 3 gives 2, minus 6, 18, minus 54, 162, minus 486, and 1458. Convergence and divergence. An important property of a sequence is if the numbers in the sequence approach a fixed value or not. If the values in the sequence do approach a certain number, then the sequence is said to converge, or the sequence is convergent. If a sequence does not converge, it is said to diverge, or the sequence is divergent. Example. Does the geometric sequence which has a equal to a half and r equal to a half converge or diverge? The sequence is a half, a quarter, an eighth, and so on, with a general term 1 over 2 to the power n, which gets nearer and nearer to 0 as n gets larger and larger. So you can say that this sequence converges as it approaches 0 as n increases. Example. Does the arithmetic sequence with the general term Sn equals 3n minus 1 converge or diverge? This is the sequence from earlier in this guide. As you can see, the numbers will keep on getting bigger and bigger as n increases. So this sequence diverges. In fact, it goes to infinity as n approaches infinity. It is common for sequences to approach plus or minus infinity, and every sequence of this kind is divergent. Example. Does the geometric sequence which has a equals 2 and r equals minus 3 converge or diverge? This is the sequence 2, minus 6, 18, minus 54, 162, minus 486, 1458, and so on, from the previous section. The numbers get alternately larger and smaller, and so it is divergent. However, the sequence does not approach either plus infinity or minus infinity. This is known as an alternating sequence because the numbers are alternately positive and negative. Other types of sequences. Not all sequences are arithmetic or geometric. For instance, you can make a sequence by starting with 1, then another 1, and then making the subsequent terms in the sequence by adding the two previous terms together. The first term S1 is 1, which is given. The second term is S2, which is also 1, which is also given. The third term is S3, which is 2, which is 1 plus 1, or S1 plus S2. The fourth term is S4, which is 3, which is 1 plus 2, which is S2 plus S3. The fifth term, S5, is 5, which is 2 plus 3, which is S3 plus S4. The sixth term is S6, which is 8, which is 3 plus 5, which is S4 plus S5. The seventh term is S7, which is 13, which is 5 plus 8, which is S5 plus S6. The 8th term is S8, which is 21, which is 8 plus 13, or S7 plus S8, and so on. This is called the Fibonacci sequence, and is one of the most famous sequences in mathematics. It is named after the Italian mathematician who used it in a book of 1202, but it was known long before this in Indian mathematics. The numbers are deeply connected to nature. For example, Fibonacci used the sequence to understand a population of rabbits. The number of spirals found in the middle of sunflowers and other flowers, as well as around pine cones and pineapples, for example, are numbers in the Fibonacci sequence. Although the Fibonacci sequence is neither arithmetic nor geometric, it can be described by the recurrence relation Sn equals Sn minus 1 plus Sn minus 2. There are methods to solve recurrence relations, and a learning enhancement tutor can go through these methods with you. The solution of a recurrence relation is the general term of the sequence. For the Fibonacci sequence, Sn equals 1 over root 5 multiplied by 1 plus root 5 over 2 all to the power n minus 1 over root 5 multiplied by 1 minus root 5 over 2 all to the power n. There are also sequences which have a pattern which cannot be written mathematically. For example, the sequence 2, 3, 5, 7, 11, 13, and so on is a list of the prime numbers, but these numbers do not follow any known mathematical pattern. In fact, mathematicians have worked on finding any patterns in the prime numbers for many centuries. Here is a table of some common sequences. Name, arithmetic. Sequence, A plus D, A plus 2D, and so on. General term, A plus n minus 1 multiplied by D. Recurrence relation, Sn equals Sn minus 1 plus D. It converges when D equals 0. Geometric sequence, A multiplied by R, A multiplied by R squared, A multiplied by R cubed, and so on. General term, A multiplied by R to the n minus 1. Recurrence relation, Sn equals R multiplied by Sn minus 1. It converges when the magnitude of R is less than 1. The plus or minus 1 sequence. Sequence, minus 1, 1, minus 1, 1, and so on. General term, minus 1 to the power n. Recurrence relation, Sn equals minus Sn minus 1. Converges? No. Uniform sequence. Sequence A, and so on. General term, A. Recurrence relation, Sn equals A. Converges? Yes. Fibonacci sequence, 1, 1, 2, 3, 5, and so on. General term, 1 plus root 5 to the power n minus 1 minus root 5 to the power n, all divided by 2 to the power n multiplied by root 5. Recurrence relation, Sn equals Sn minus 1 plus Sn minus 2. Converges? No. Prime number sequence, 2, 3, 5, 7, 11, and so on. General term, none. Recurrence relation, none. Converges? No. Further guidance and information. If you have any further questions about mathematical skills or would like to discuss any other aspects of mathematics, you can talk to your lecturer or personal advisor or make an appointment to see a learning enhancement tutor in the Dean of Students office. You can telephone 01603 592761, email dos.help@uea.ac.uk, or visit our website at www.uea.ac.uk/dos/let. There are further resources on many other aspects of numeracy, mathematics, statistics and science available from the Dean of Students Office and on its website. These include questions to practice, model solutions and webcasts illustrating essential skills. This guidance is one of a series on mathematics produced by the Dean of Students Office at the University of East Anglia.